In section 2.7, it's prove angle pair relationships. So we're going to look at some theorems and a postulate that are going to give us angle relationships that we can work with. So the focus is going to be proving the theorems that we have, getting more practice with proofs, and then we'll finish up with a couple of proofs as well. So our first one is theorem 2.3, and that is the right angle congruence theorem. And that tells us that all right angles are congruent. So if we write that out, it says if I have, now let's say we have two angles, and they're both right angles. That tells us, this theorem, that if angles 1 and 2 are right angles, then they are congruent. So if angle 1 and angle 2 are right angles, then they are congruent. So we can say angle 1 is congruent to angle 2. So we need to prove that. Now, it's a statement that seems pretty obvious, but if we think of what makes it obvious, we could say, well, right angles, we know they're 90 degrees, and if two angles are both 90 degrees, they're going to be equal to each other, which means they're congruent. So that thought process that makes us think, yeah, it works, is actually the basis for our proof. So, we're starting with that angle 1 and angle 2 are right angles. We want to prove that they're congruent. So, if we're doing a flow chart, I'm going to say angle 1 and angle 2 are right angles. Then if I said, well, what is a right angle? And you would hopefully know that a right angle means that the measure of angle 1 equals 90 and the measure of angle 2 equals 90. And what tells us that is the definition of right angles. So, what are right angles? Well, they're angles that equal 90 degrees, and that's by the definition. So, next thing we have is, well, they're both equal to 90, so that means they're equal to each other. And that's a property we've talked about quite a bit in the last few sections. That is the transitive property of equality. But we're here at equal, we want congruent. We need to make that last jump that angle 1 is congruent to angle 2, and that lets us jump from equal to congruence, and that is the definition of congruence. You could be more specific and say the definition of angle congruence or the definition of congruent angles, but definition of congruence works as well. So we pieced it together and made that formal argument that says if 1 and 2 are right angles, then they are congruent. Our next two theorems are actually very related to each other. We have the congruent supplements theorem, and that says if two angles are supplementary to the same angle, then they are congruent. So I have three angles here, and I see that if angle 1 and angle 2 are supplementary, and angle 2 and angle 3 are supplementary, then angle 1 is congruent to angle 3. So, I have supplementary angles. I have supplementary angles. That means these two angles are going to be congruent. The two angles that have the same supplement is another way we could think about it. Now, that is very close to this theorem, the congruent complements theorem, which follows the same idea. If two angles are complementary to the same angle, then they are congruent. So I could say if angle 1 and angle 2 are complementary, it's going to abbreviate, and angle 2 and angle 3 are complementary, then angle 1 is congruent to angle 3. So basically the same thing. The only thing we changed out there was the supplementary and complementary terms. And if we look at these two, they're really the same idea. These two angles add up to 90. These two angles add up to 90. But since 2 is the same in both, these two are going to be equal. So they're the same idea in both of them. So we're really going to only look at one of those proofs. So let's look at the congruent complements theorem. So we'll do this proof. So we'll just bring this down and use it here. So we're given angle 1 and angle 2 are complementary. Angle 2 and angle 3 are complementary. We need to prove angle 1 is congruent to angle 3. So anytime we do a proof, the first thing we list is our given, and that's this right here, so we're just going to write it again. I realize we are writing it a lot, but angle 1 and angle 2 are complementary. We'll abbreviate this time. Angle 2 and angle 3 are complementary. That's given. And we want to get to angle 1 is congruent to angle 3. Move it up here. So, we have complementary angles. We want to show that 1 and 3 are congruent. First thing I would start with is, well, they're complementary. What does that mean? That means that the measure of angle 1 plus the measure of angle 2 equals 90 degrees, and the measure of angle 2 plus the measure of angle 3 equals 90 degrees. And that goes back to if I asked you and said, what are complementary angles, you would hopefully tell me this. So that is our definition of complementary angles. Okay, and we want to get here. So we kind of have some extra stuff here, but if I notice, both of these terms are equal, or have 90 in them. 1 plus 2 and 2 plus 3 are both equal to 90. So that means we could write it as the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3. And that's a property that goes back to saying if they're both equal to the same thing, they're equal to each other, and that is transitive property. Okay, now we're getting closer. So I have 1 plus 2 equals 2 plus 3. I want to get to 1 and 3. Just 1 and 3. Now, I want to get to their congruent, but if I can first get to them being equal, it'll be an easy last step. So my next step is I'm going to subtract the common piece from both of them that I don't need. I don't need angle 2. So I'm going to subtract that, and that's because angle 2 is equal to angle 2. We could mention it is reflexive property off to the side. But that gets me to angle 1 equals the measure of angle 3, and that was subtraction. And then my last step, I get to them being congruent. And that's an important one. I think I mentioned it already earlier. If they're equal, they're congruent, as well as if they're congruent, they're also equal. That is our definition of congruence. So we've worked our way through, we've made that logical argument. They're complementary. That means they add to be 90, but we had 90 in both of them, so we used transitive to put the two parts together. We subtracted the common terms from each side, which was angle 2. That got us to measure of angle 1 equals the measure of angle 3, and then we can say if they're equal, they are also congruent by the definition of congruence. Now, we jump back to the congruent supplements. If we were talking about supplements, we would make this supplementary, we'd make this 180, and everything else would follow the same process. Of course, that would say supplementary as well, but it'd be basically the exact same proof. So let's move on to our next one. And this is the linear pair postulate. It says if two angles form a linear pair, then they are supplementary. So if I have angle 1 and 2 there, I'd say if angle 1 and angle 2 are a linear pair, then they are supplementary. Okay, it is a postulate. We do not have to prove it. We just accept it as fact. And this kind of fits when we talked about originally a linear pair is a supplementary angles and are adjacent. So we just kind of formally state it now so we can use it. But one thing to look at while we're here, let's think back earlier in this chapter we talked about the converse. So if I wrote the converse of this, I would say if angle 1 and angle 2 are supplementary, then they are a linear pair. So this we can accept as true because it's a postulate, but let's look at this one. If 1 and 2 are supplementary, then they're a linear pair. At first, it makes sense. Supplementary angles, they do work with linear pairs. But this one is false, actually, and we have to look at a counterexample. And that's one when I have supplementary angles, but not a linear pair. So let's say I have this angle here is 60 degrees, and I have another angle that is 120 degrees. Those two angles are supplementary because they add to equal 180. But they are not a linear pair, and that is because a linear pair has to have adjacent angles. They have to share a side, share a vertex. These two angles here are a linear pair. There's their vertex, there's the side that they share. These two, they're not adjacent. Now, relative to the paper, they are next to each other, but that's not enough to say that they are in fact adjacent. So, share side, share vertex, so this is false. This statement's true, the converse is false. And this also goes back to the real difference between supplementary angles and a linear pair of angles. A linear pair must be adjacent. Supplementary angles, it doesn't address whether they're adjacent or not, so you have a counterexample to that. Okay, so our next theorem is the vertical angles congruence theorem, and this tells us that vertical angles are congruent. So let's label here. Let's call this 1, 2, and 3. So here I'm going to say if angle 1 and angle 3 are vertical, then angle 1 is congruent to angle 3. Now, I've listed 2 there. 2 is not vertical to either 1 or 3. It is adjacent to both of them. It is actually a part of a linear pair for both. It's a linear pair with 1 and 2, linear pair for 2 and 3, but 2 is not involved. These are the congruent ones. So again, vertical angles, like we've talked about before, when two lines intersect, they're on opposite sides. We have to go through the vertex. Their sides also form opposite rays. So let's look at the proof for this one. We're going to start with angle 1 and angle 2 are vertical angles. This is our given. I guess I should write our given a little more formally, and we're trying to prove. Okay, so that is what we start with. We want to get to here. Well, we know they're vertical angles. We can't say they're congruent because that's what we're proving. So there's not much we can do with just that. But I mentioned why would we list angle 2? And sometimes we get that idea when we look at a proof. Why would they give us that other labeling part? Maybe it's a hint we do need to use it. So I actually know that angle 1 and angle 2 are a linear pair, as well as angle 2 and angle 3 are a linear pair. Now, what allows us to mention that? It's, frankly, the definition of a linear pair. Okay, so if they're a linear pair, like we just talked about, we know that they are supplementary. That was our linear pair postulate. So I'm going to say angle 1 and angle 2 are supplementary, as well as angle 2 and angle 3 are supplementary. our reason to that is the one we just mentioned again, linear pair postulate. So, these are now supplementary. I still need to get from 1 to 1 is congruent to 3, and that's actually another theorem we've talked about today. Notice how 2 is in both of them. If 1 and 3 have the same supplement, or they're supplementary to the same angle, then they are congruent. That is our congruent supplements theorem. Guesses to the fact that vertical angles are congruent. And that's going to be a big one we are going to use often. So let's look at some examples. So I have this diagram here, 1, 2, 3, and 4 are my angles. I'm given angle 1 is 112. I need to find the other ones. Right off the bat, we should recognize vertical angles are the same, so angle 3 is also 112. Now I need 2 and 4. Now we realize 2 and 4 are going to be the same because they are vertical, but first we have to find one of them. So the fact that they're vertical doesn't give us the answer. The fact that they are supplementary to either angle 1 or angle 3 means we can do 180 minus 112 and get 68, which would be both of the angles. So given one angle in this case, I can find all of them. We go to another one. This one, we're given that 2 is 67. Right off the bat, we should know 4 is also 67. And then to find 1 and 3, it's 180 minus 67, which is 113. Now, that's just a basic type. Let's say I added some more to it. Let's make it a little more of an algebra problem. And I'm not so much worried about the solution here, but more about the setup, because there's really two types you're going to see, and these are very common setups for problems. So let's say I have one, let's write some terms here. Let's say 3x plus 2, 4x minus 1, 5y minus 6, and 3y, just 3y. Okay, here's the problem. Here's your setup. You need to solve. Now, we know vertical angles are equal. And so in this case, I could say that 5y minus 6 equals 3y, dot, 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 and solve for y. I could say that 3x plus 2 equals 4x minus 1, dot, 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 solve for x, and we get an answer. Really right here, the answer I'm not too worried about. You can solve that answer and get to it. But what I want you to realize is you use those vertical angles to solve. I wouldn't use the supplementary angles here because this one's a y, this one's an x, y and x, y and x, x and y. They don't match up. I can't solve with them. So even if I did add them and set them equal to 180, it's not going to help me. Now, this, if we took it to the problem, another problem, and kept the same terms, but notice this time I'm switching 4x minus 1 and 3y. Now the problem changes, so it's linear pairs. So now the verticals don't work for us. It's the fact that 5y minus 6 plus 3y equals 180, dot, dot, solve for y, 3x plus 2 plus 4x minus 1 equals 180, and we solve for x. It's a different problem. So you're going to see these types of problems often, but you have to make sure you differentiate to which type it is. If they're vertical to each other, you set them equal. If they're adjacent, if they're linear pair, if they're supplementary, you add the two and set it equal to 180. And it's just taking those quick few seconds to make sure you get that right setup. It means you're going to get to the right answer. Assume over here we add and set equal to 180. It's not going to work. We're not going to get the right answer. Over here, if we automatically just set them equal between these two, that's not going to work. We have to make sure the setup is good. Okay, let's finish with a couple of proofs. One of them has to do with angles, which we've talked about angles a little bit today. The other one has to do with segments, and this is more just review to pull in and get us more practice from this whole chapter. So, I'm given that angle 1 is equal to angle 3. And I need to find that the measure of angle DEG is equal to the measure of angle HEF. So if we just look at what we have, we know this angle and this angle are the same. We want to find that this angle, let's just make dotted lines, this angle and this angle are the same. So if we look at what we have so far, these two are the same. If I was to add 2 to this, it gives me this angle. If I was to add 2 to 3, it gives me this angle. But 2 is the same in both. So I could add it to both of them, and it gives me the same value. It doesn't change the fact it's equal. That's the thought process we have to this problem. But now we have to demonstrate that process and form that logical argument. So what I want to get is I want to get 2 added to both sides. So I'm first going to say, let's put the measure in front of those. The measure of angle 2 equals the measure of angle 2. And we should know that as reflexive property. And we should also know, typically when we do reflexive property, we're going to add it then to a statement. So the measure of angle 1 plus the measure of angle 2, the measure of angle 2 plus the measure of angle 3. And the reason we can do that is addition. It's the addition property of equality, not to be confused with angle addition, which is adding up the parts, setting equal to the whole. Okay. So now that I've added, I have 1 plus 2 equals 2 plus 3. If I look, 1 plus 2 is actually the same as DEG. 2 plus 3 is actually the same as HEF. So this actually matches. We need a way to connect it, though. This is named by the numbers. This is named by the letters. So we have some way to connect it. What we're going to do is to find a way to rename them. Now, we know that the measure of angle DEG is equal to the measure of angle 1 plus the measure of angle 2. We know that. We also know that the measure of angle HEF is equal to the measure of angle 2 plus the measure of angle 3. What we need is a reason that lets us say that. And I hinted at it earlier. It's not the addition property. It's actually angle addition postulate. In the angle addition postulate, it says the entire angle is equal to the sum of the parts, or I can add up the parts to equal the whole. So this is going to let me change this statement to rename it as the whole thing. And the reason I can do that is I'm just replacing it or using substitution. So if we look at the flow of this proof, start with what I was given. I added the same thing to both sides. I renamed the angles. I used reflexive to allow me to add to both sides. I used angle addition to allow me to change the names of them. But it's the main flow of this proof is given, add to both sides, change the name. It's where you want to finish. Okay, if we at least see that process, we're off to a good start. Okay, we go to our last one. Kp is equal to St. PR is equal to TV. So let's mark that. We'll write these out. Kp equals St. PR equals TV. And we want to get to Kr equals SV. Let's make a little. I want to show that is equal to that one. Now, we look at this problem. If I add this segment plus this segment, and I add the same segment, same length, to the other segment with the same length, it's going to give us the same total. So it's kind of an obvious proof to see. Even if I asked you to explain it out, you probably could. You could put numbers in there, use a specific example, but we need that logical argument. So we still need to figure out ways to get there. We're going to kind of follow this same idea we did up here. So what I'm going to do first is I'm going to focus on this one. Kp equals St. Now, I need to add something to both sides because I want to build it up so I have the whole thing. I don't know yet what to add, so I'm just going to say PR equals PR. Because that's reflexive property, and like we've said with reflexive property, whenever we mention it, we want to add to both sides. So I could do that, and I get that KP plus PR equals ST plus PR. Now, if you're not quite sure why we did that, we'll see why in a second, why it does connect. This is addition property of equality. So I've added PR to both sides. I needed to add a value. I couldn't add this to both sides. We'll get there eventually, but we can't just directly add it to both sides. So we start here. So KP plus PR, KP plus PR, ST plus PR, ST plus PR. Well, wait a minute. This doesn't seem to make sense because they're not on the same line. It would be better almost if we had a way to make ST plus what it's with, which would be TV. And we actually know that PR and TV are the same. So we're going to replace this with TV. Now whenever we replace, we substitute. So I'm going to substitute PR for TV, and that's substitution property. So now we have KP plus PR equals ST plus TV, and we look at our end result we want, which is KR equals SV, and this, KP plus PR, is the same thing as KR. ST plus TV is the same thing as SV, we just need to change the name. So right now we're close, we just need to connect it. Now, what we did up above, we used angle addition to change the names. We had parts, we wanted the whole thing. Here, we have parts, we want the whole thing. So it's not angle addition this time, it's going to be segment addition. So that's KR equals KP plus PR, as well as SV equals ST plus TV. And that is segment addition postulate. Now that we have those, we can connect it, replace this out, and it's going to be substitution property that gets us to where we want to be. So it's the same process again. We added to both sides, we substituted, but we need that connection. What's going to get us from the parts is equal to the parts to the whole thing is equal to the whole thing. Segment addition postulate was the key. And you're going to notice we have key things in both of these proofs we're going to see often. We have angle addition, segment addition, they help us change the names. We had addition property after reflexive, so it allowed us to add to both sides. Down here we had to substitute once we did that to make things match. But the flow of the proof, on the second one, is through. What we're given, we add to both sides, we fit so the parts go to each segment, and then we change the name to get to our end result.